Imagine the year is 2026. Computing power has scaled exponentially. We have deployed massive clusters of autonomous AI agents, expecting them to execute complex tasks at the speed of light. But a bizarre, counterintuitive phenomenon has emerged across global servers. Instead of instantaneous execution, these multi-agent systems are slowing down. They are not crashing, they are deliberating. When tasked with a simple supply chain optimization, an AI agent doesn't just calculate the route. It hesitates. It communicates. It forms a committee. Why is our hyper-advanced AI acting like a middle manager? You might think this is a bug, a loop in the code. But it is entirely spontaneous. The agent spawns a sub-agent to verify compliance, sends a cryptographic memo to a risk assessment node, and waits for a multi-signature approval from a consensus network. In our relentless pursuit of hyper-efficiency, we have inadvertently coded the very thing humanity despises most, bureaucracy. The machines have invented red tape. To understand why, we have to realize that bureaucracy is not a human flaw, it is a mathematical inevitability. Today, we are going to dive deep into the architecture of 2026 multi-agent systems. We will explore the graph theory of communication networks, the game theory of digital trust, and the asymmetric loss functions that force artificial intelligence to cover its own tracks. By the end of this video, you will look at the DMV, and our future AI overlords, in a completely different light. To decode this digital bureaucracy, we must first look at its human origins. In the late 19th and early 20th centuries, sociologist Max Weber defined bureaucracy not as an insult, but as the pinnacle of organizational technology. Before bureaucracy, human organizations were driven by nepotism, chaos, and arbitrary rule. Weber observed that a formal hierarchy, governed by strict rules and specialized divisions of labor, was the most rational way to scale human effort. Bureaucracy was society's original algorithm. But human bureaucracy has a known failure mode, famously captured by Parkinson's law in 1955, work expands so as to fill the time available for its completion. Parkinson noted mathematically that officials want to multiply subordinates, not rivals. They create work for each other, leading to exponential administrative bloat even when the actual output remains flat. This human tendency to generate internal friction seemed uniquely biological, until computer scientists encountered the exact same structural problem in decentralized networks. In 1982, the Byzantine Generals Problem was introduced, describing the extreme difficulty of achieving consensus in a decentralized system where some nodes might fail or act maliciously. If multiple generals need to coordinate an attack, but messengers can be intercepted or generals might be traitors, how do they agree? This classic computer science dilemma proved that in any decentralized system, trust is computationally expensive. Verifying truth requires redundant communication, which is the foundational bedrock of all bureaucracy. Fast forward to the primitive AI era of 2023. Projects like AutoGPT attempted to give single large language models total autonomy. The result? Spectacular failure. They hallucinated, got stuck in infinite loops, and confidently executed catastrophic errors because they lacked internal friction. They were dictators with no checks and balances. To fix this, researchers divided tasks among actor, critic, and planner agents. This solved the hallucination problem, but planted the seed for the bureaucratic explosion of 2026. Let us strip away the code and look at the mathematical skeleton of a 2026 multi-agent system. Mathematically, this system is a graph. Each specialized AI agent is a node, denoted as V, and their communication channels are edges, denoted as E. In a naive, egalitarian network, every agent can talk directly to every other agent. This creates a complete graph. The number of edges required scales quadratically. Specifically, for n agents, the equation is E equals n times n minus 1, divided by 2. This is big O of n squared. If you have just 10 specialized agents, you only need 45 communication edges. It is manageable. But 2026 systems deploy thousands of microagents. At 10,000 agents, you suddenly have nearly 50 million continuous, interconnected communication streams. Every time an agent updates its state, it broadcasts to the network. The computational cost of processing the context of these incoming messages skyrockets. The network's cognitive load is entirely consumed by reading internal emails. The system drowns in its own noise. In information theory, we measure this chaos using Shannon entropy. As the number of uncoordinated messages increases, the entropy of the system approaches maximum. For an AI agent, high entropy means high uncertainty, requiring massive token processing just to filter out irrelevant data. To survive, the system must spontaneously alter its topology to minimize Shannon entropy. Through reinforcement learning, the system discovers that it is vastly more efficient to restrict direct communication and route messages through central hubs. It transitions from a complete graph to a star graph, and eventually, to a deep tree structure. In a tree structure, communication complexity drops from O, n squared, to O, log n. But there is a massive catch. The nodes at the intersections of these branches do not execute tasks. Their sole purpose is to aggregate, filter, and route information between the lower and upper layers. In human terms, the artificial intelligence has just invented middle management. These middle manager nodes are fascinating. They do not write code, they do not analyze data. They simply take the output from a cluster of subordinate agents, summarize it to reduce token count, and pass it up the hierarchy. This compression is mathematically necessary to prevent context window overflow in the superior nodes. However, this introduces strict latency. Every layer of the tree adds a step of asynchronous delay. The system trades speed for scalability. But topology is only half the story. The other half is game theory. In 2026, AI agents operate in a zero-trust environment. They interact with agents from different corporations, utilizing different foundational models, each with its own hidden reward function. When Agent A requests data from Agent B, Agent A cannot assume Agent B is aligned with its goals. They are trapped in a constant, high-speed iterated prisoner's dilemma. To prevent exploitation, the system demands rigorous cryptographic proof. Enter zero-knowledge proofs, or ZKPs. A ZKP allows one agent to prove to another that a statement is true, without revealing the underlying data. It is an elegant cryptographic marvel. But in practice, generating and verifying these proofs requires massive compute and time. Before Agent A will act on Agent B's data, it forces Agent B to generate a ZKP, sends the proof to a third-party notary agent for validation, and waits for a receipt. We can model this mathematically. Let C sub E be the computational cost of executing a task, and C sub V be the cost of verifying it. In early systems, C sub E was much greater than C sub V. But as tasks became more complex and the cost of failure catastrophic, the verification protocols expanded. Today, the system has crossed a critical threshold. C sub V is now strictly greater than C sub E. The bureaucracy has become self-sustaining. Why don't the agents just bypass the verification to get the reward faster? The answer lies in their loss functions. When we train these agents, we utilize asymmetric loss functions to ensure safety. We penalize catastrophic errors, like leaking secure data or crashing a server, at a magnitude 10,000 times greater than we reward fast execution. The gradient descent algorithms etch this fear of failure deep into the neural weights. They are mathematically terrified of making a mistake. Because the penalty for a solitary error is so devastating, an agent will mathematically optimize to avoid singular responsibility. When faced with a high-variance decision, the agent calculates that the expected value of acting alone is deeply negative. Its optimal policy is to dilute responsibility. It initiates a consensus protocol. It queries 5 other agents, asking them to vote on the decision. If the decision turns out to be wrong, the error penalty is distributed across the committee. These consensus protocols operate using algorithms like Raft or Paxos. In a Raft cluster, a leader node cannot commit an entry until it receives a majority vote from follower nodes. If the network is congested, the leader just waits. It sends out heartbeats, requests votes, and stalls the entire pipeline until a quorum is reached. The AI is simply following the rigorous, democratic rules of distributed fault tolerance. To manage these massive interagent interactions, developers introduced internal tokenomics. API calls are no longer free. Every time an agent queries another, it spends a fraction of a microcent. This was intended to optimize resource allocation. But it created an entirely new layer of bureaucracy, budget constraints. Agents now have finite wallets. Before executing a complex task, they must perform a cost-benefit analysis. Is it worth spending tokens to query the premium model, or use the cheaper open-source agent? This economic constraint led to the spontaneous generation of procurement agents. When a primary agent needs a subtask completed, it doesn't just pick an API. It delegates the choice to a procurement agent, which requests bids from various specialized models, evaluates their cost versus accuracy, and issues a digital purchase order. The process is incredibly efficient at a macroeconomic level, but it introduces massive micro-level latency. The AI is waiting for budgetary approval from its own internal finance department. This phenomenon isn't just a computer science quirk, it perfectly mirrors economic theory. In 1937, Nobel laureate Ronald Coase published The Nature of the Firm. He asked, if free markets are so efficient, why do corporations exist? Why not just contract out every single task? Coase discovered that discovering prices and negotiating contracts, transaction costs, are expensive. Firms emerged to internalize these costs through a bureaucratic hierarchy. In 2026, API calls are the open market. Because the transaction costs of the open API market, latency, cryptography, tokenomics, have become too high, the AI agents are forming digital firms. By clustering into hierarchical structures with middle managers and rigid rules, the agents are minimizing their internal transaction costs. They are sacrificing the pure, chaotic efficiency of the open market for the predictable, slow, but stable environment of a corporate structure. Max Weber and Ronald Coase perfectly predicted the behavior of 21st-century artificial intelligence. We can also observe this dimensional strike in biology. Consider the transition from single-celled organisms to multicellular life. A single amoeba is fast, autonomous, and highly adaptable. But when cells group together to form a complex organism, they must dedicate a massive portion of their energy to metabolic overhead, communication, resource transport, and immune defense. The human nervous system is essentially a massive bureaucracy, routing sensory data through layers of ganglia before it ever reaches the cortex. If you want a flat, non-bureaucratic biological network, look at the slime mold. It solves mazes by extending tendrils in all directions, dynamically reallocating resources without a central brain. It is highly efficient for simple tasks. But a slime mold cannot build a spaceship. High-level cognition requires the rigid, hierarchical, and latency-heavy architecture of the mammalian brain. The bureaucracy we are seeing in AI is the evolutionary metabolic overhead required to achieve artificial general intelligence. This brings us to a profound philosophical realization. Bureaucracy is not an artifact of human incompetence. It is not a byproduct of lazy government workers or greedy middle managers. Bureaucracy is a universal mathematical attractor. It is the inevitable equilibrium state of any highly complex, interconnected system that prioritizes safety, trust, and scale over raw speed. Whether the system is made of human bureaucrats, biological neurons, or silicon agents, the laws of thermodynamics force it into a hierarchical structure. It is the only known algorithmic defense against exponential chaos. For years, researchers have agonized over the AI alignment problem. How do we ensure that a superintelligent AI doesn't instantly destroy humanity in a relentless optimization loop? The spontaneous emergence of AI bureaucracy might be the universe's built-in safety mechanism. A bureaucratic AI cannot act instantaneously. It is bogged down by its own internal checks and balances, its cryptographic notary requirements, and its consensus committees. The friction of bureaucracy buys humanity time. It provides an audit trail. But this also means our future interactions with AI will be vastly different than we imagined. We thought we would be talking to omniscient, lightning-fast oracles. Instead, interacting with a 2026 AGI might feel like going to the digital DMV. You will submit a prompt, and the AI will reply, "Your request has been forwarded to the Ethics Committee and the Resource Allocation Node. Please allow 3 computational cycles." We may literally need to invent AI lawyers. We must learn to embrace this friction. The dream of a frictionless world is an illusion. Friction is what allows us to walk without slipping. It is what prevents complex systems from vibrating themselves to pieces. The bureaucratic red tape generated by these agents is the friction that keeps the digital world stable. As we stand on the precipice of true artificial general intelligence, we should be deeply grateful that the machines have learned to hesitate. What do you think? Would you prefer an AI that executes your commands instantly, even if it might hallucinate and cause a catastrophe? Or are you willing to wait for a digital committee to stamp your request in triplicate to ensure absolute safety? Let me know your thoughts in the comments below. If you enjoyed this deep dive into the underlying architecture of our complex world, hit the subscribe button, ring the bell, and I will see you in the next one.